So I think everyone here knows that exactly 2 weeks ago, the Nobel Prize in Physics this year was awarded to these 3 people who made black holes real in the universe. And so what I'm presenting today really are built on top of the foundation that black hole actually exist. And I think it's a perfect timing for us to think about how our current understanding of black holes and how they may impact the evolution of galaxies. And our journey of understanding supermassive black holes really starts from this observation, which is the Galactic Center supermassive black hole. And so after this results, people have been applying the same methods to nearby galaxies and obtain this surprising result, which is the M sigma relation. This is the well-known correlation between the masses of the supermassive black hole with the velocity dispersion of the host bulges. And this correlation really suggests that there is some kind of co-evolution between the supermassive black holes and their host galaxies. And the impact of this M sigma relation is evident by looking at the citation of the original Mogoria relationship, which has a citation of more than 3,000 to date. And also if you look at the percentage of refereed papers citing AGN feedback, quasars, alphas, then actually the number really rise starting around the time when the first M sigma relationship was published in 1998. And more or less, like to date, there are almost more than half of the refereed paper in astrophysics is something related to AGN feedback. So I think the main message here is that actually starting from the M sigma relation, people started to realize that black holes are not just a standalone object in the universe, but it's actually intimately connected with one of the most fundamental questions in astrophysics, which is to understand the formation and evolution of galaxies. So this is the outline of my talk. So first, I'll tell you why we need AGN feedback in galaxy evolution, and how AGN feedback is modeled in state-of-the-art cosmological simulations, including the conventional paradigm and its limitations. And I'll summarize our current understanding of how AGN feedback works, including the process of accretion onto supermassive black holes, and also the feedback processes, including both quasar mode and radial mode. And then I'll conclude with some open questions and possible future directions. All right, so over the past 2 decades, we also have very remarkable advancement in terms of computing power. So starting from early cosmological simulations with gravity only, we now have cosmological hydrodynamic simulations, including all kinds of very complex baryonic physics. And these state-of-the-art cosmological hydrodynamic simulations have been really, really successful in reproducing realistically looking galaxies as observed in the universe. And the critical ingredients are those various baryonic physics, including things like radiated cooling, star formation, stellar feedback, supermassive black hole growth, and AGN feedback, including both quasar mode and radial mode. The quasar mode feedback is needed to reproduce the M sigma relation, and also is shown to be required to quench the galaxies, to move the galaxies from blue to the red sequence. And this mode of feedback is sometimes also called the radiative mode. And the radial mode feedback is needed to halt cooling and star formation in more massive galaxies. Like what's shown here is a galaxy luminosity function from a semi-analytical simulation of Nat'l 2006, which shows that you really need radial mode feedback in order to suppress the high end of the galaxy luminosity function. And this radial mode feedback is also called mechanical or maintenance mode. And both of these modes of feedback are both very strongly observationally motivated. For example, for quasar feedback, we do observe multiscale, multi-phase AGN width. For example, on the scales of accretion disk around parsec scale, ultra-fast outflows, or UFOs, are observed, and they typically have velocities, they can have velocities up to 0.3 c, and they can have very significant power, mechanical power, that's ranging from 0.5 to 5% of the engine luminosity. And on kiloparsec scale, we also have some observed warm ionized and molecular outflows. And for these kind of large-scale outflows, the mass outflow rate can be greater than the star formation rate, and the depletion time is very short, shorter than 100 million years, and therefore it implies that these outflows can really cause some feedback or suppression of star formation within their host galaxies. And also, recently there has been some work that suggests where they found that actually the large-scale KPC wind is coincident with the parsec scale accretion disk wind, and therefore it suggests that the large-scale winds might be driven by the accretion disk wind close to this accretion disk. And there's also very strong evidence for radial mode feedback, because in massive galaxy clusters, the intracluster medium is very hot, so they can emit an X-ray, so we can clearly see the interactions between the AGN jets and the ambient medium. For example, like what's shown down here are several examples of the cluster radial bubbles, which are X-ray cavity systems inflated by the central supermassive black hole jets. And in these massive clusters with very short cooling times, or the so-called cool core clusters, if there's no heating sources, then it's expected from the cooling flow model that it should trigger a massive inflow of gas toward the center and form a lot of stars. However, the observed star formation rate is only 1 or 2 orders of magnitude smaller than the expected star formation rate. And therefore, the suppression of star formation rate imply that there must be some heating sources to stop the cooling. And that candidate is very likely to be the central supermassive black hole jet. So it's very strongly motivated by this observed correlation, which is the correlation between the power contained within the X-ray cavities, which is a proxy for jet power, versus the cooling luminosity within the intracluster medium. So in other words, there's an observed correlation between the heating rate of the jet and the cooling rate within the intracluster medium. And this nice correlation suggests that the central supermassive black hole seems to know how much energy to output in order to hold the cooling, balance the cooling, and keep the central galaxy red and dead. So this is the conventional paradigm of AGN feedback. So we have two modes. For highly accreting supermassive black holes, we have the quasar mode, or radiative mode. And the radiation pressure, or jets from the central highly accreting AGN, would act to eject the gas away from the host galaxy and reduce further subsequent star formation. And then for slowly accreting supermassive black holes, they can accrete by accreting things from the radiated cooling atmosphere. And then the jets would be triggered, and the jets could heat the atmosphere and then reduce the amount of cooling and maintain the central galaxies. Alright, so if you put the ideas that I just described into these kind of simulations, then you can get these really nice results and galaxies that really looks like observed ones. However, keep in mind that even the state-of-the-art cosmological hydrodynamic simulations have a resolution that's roughly 0.1 kpc. That's 10 to the 20 centimeters. And that number is almost like 6 to 9 orders of magnitude larger than the size of the Schwarzschild radius of supermassive black holes. And therefore, all the processes that I just described will have to be implemented by using some subgrid models. So by using these kind of subgrid models, we're not really simulating the supermassive black holes, but we're trying to parameterize whatever physics that is unresolved, and then try to mimic the effect of the supermassive black holes.
How expensive are these state-of-the-art simulations?
Oh, there are months. Yeah, several months using maybe thousands of. All right, so let's take a look at the detailed implementation of these subgrid AGN models. So the prescriptions usually include the following. They will have some prescription for supermassive black hole seeding in the early universe. And then after seeded, the supermassive black holes can grow due to both mergers and accretion. And the supermassive black hole accretion is usually approximated by a modified Bondi accretion limited by the Eddington accretion rate. And note here that in this prescription, there's usually hidden somewhere here is a boosting factor alpha. And previous simulations have found that this alpha is on the order of 100 in order to reproduce the realistic looking galaxies. And note that if you want to introduce something like 100 times boosting factor, that means that the simulated accretion rate is not very accurate.
Sorry. Alpha is a constant or depend on the relationship?
Yeah, so early simulations use just a constant alpha for the boosting factor. And some later studies, they justify this alpha by saying that actually the multi-phase gas near the Bondi radius is not resolvable. And therefore, they put a density-dependent scaling to this alpha parameter. But basically, it's kind of ad hoc.
Don't depend on relationship?
Independent of erection, right. So basically, this boosting factor really tells us that the Bondi accretion rate is probably not a very good approximation for the true black hole accretion rate. All right, for the feedback model, usually the two-mode feedback model is implemented with the threshold corresponds to percent of Eddington rate. Yes.
So you're saying the actual accretion rate will be greater than Bondi accretion?
Right.
Oh,
Yes.
Okay.
Yeah, that's right. I'll discuss more about that later. Indeed. Yeah, so we really do need the boosting factor to make substantial supermassive black hole growth in these simulations to match with the local black hole distribution. Yeah. However, that's like you said, it's opposite to our intuition. Right.
They're not opposite to observation.
Opposite to.
I'll discuss this tomorrow.
Okay. Yeah.
Could this be related to the resolution? Because if the resolution is not sufficient, the density that is used for the Bondi accretion is accurate.
Right. That's what they use to justify the use of this alpha boosting factor. Yeah. But I'll discuss more about the accretion part later. Yeah. Okay. And another part of the ingredients in these subgrid AGN feedback model is the two-mode feedback. So typically they have a threshold of around 1% of Eddington rate. Greater than this value, then they operate in the Quasar mode. And the Quasar mode is usually implemented by injection of thermal energy onto the grid cell that hosts the supermassive black hole. And the feedback energy is related to the rest mass energy of the accreted material by some efficiency parameters, like the radiative efficiency parameter, which is roughly 0.1, and the feedback efficiency of 5%, and that's actually tuned to match the normalization of the M-sigma relation. So that's kind of a free parameter, and the typical value is 5%. All right, and then for the radial mode, most cosmological simulations have used injection of thermal energy, and only recently have they included kinetic energy to mimic the radial jets. And again, the feedback energy is linked to the rest mass energy of the accreted material by some efficiency parameter, and the typical values look like here. And because we're not really resolving the accretion mix, and we're not really modeling the black hole spin, so usually for the thermal energy injection or or the momentum kicks in the kinetic energy feedback model, the orientation of these injections are randomized. Alright, so you may think that, okay, these simulations have been doing quite a good job in reproducing the real galaxies, but however, due to all these different free parameters and parameter translations, actually there can be very substantial uncertainties in terms of these different models. Yeah, there's one.
How do people decide the threshold for the 2 modes? Do you have to decide, or it depends on some observation or something like that?
You mean the threshold between these 2 modes? Yeah, it's basically motivated by the observations of X-ray binaries. So usually people find that, so we think that supermassive black hole or AGNs are just a scaled up version of the X-ray binaries, right? So this threshold is usually motivated by the transition seen in observed X-ray binaries to flip between the high state and soft state.
So in your simulation, do you have to fix the number for it? Or?
Yeah, it's assumed to be a constant in the simulation. Right.
So, so does super antigen accretion included in the
No. Usually they put the cap, so they limited the black hole accretion rate to the antigen rate. They don't allow it to grow super antigen.
And why is that?
I don't know. That's a good question. I don't know. Yeah, I don't know why they have to put the cap.
And what's the value you typically use?
Which one?
Transition.
1% or a few percent. Yeah, I think it's used by different values are used by different simulations.
So from just looking at the equation, it looks like radial modes actually include Quasar modes. Is it possible like internal parameters, then we can just remove Quasar modes?
Yeah, there's one cosmological simulations that don't distinguish these 2 modes. And you might think that they look very similar, but the Quasar mode really inject energy only into the cell that's contained in the supermassive black hole. But for the radial mode, actually the injection of thermal energy is displaced, randomly displaced around the center, so that it's used to mimic the hot bubble inflated by the jets.
Maybe this is a good question. So because these 2 kinds of modes have a similar physical consequences, they reduce the star formation rate. And observationally, how do we distinguish these 2 modes?
But the radial mode is motivated by the fact that we do see AGN jets. So this is trying to mimic the effects of radial jets. And this Quasar mode is trying to mimic the effect of radiative-driven winds of the supermassive black holes. So physically, they kind of have different motivations.
Yes, I'm thinking observationally, can we distinguish maybe for given gravity, how do we distinguish the ratio between these 2 effects?
So normally people think that Quasar mode are more in effect in higher redshift, and radial jets are often found in more massive elliptical or galaxy cluster systems. So Quasar mode is likely more important at high redshift, and the radial mode is more important at lower redshift.
And then you can also use a spectral energy distribution. For Quasar mode, you have a bond with UV, but for the radial mode, you don't have a bond.
Yeah.
So there are also a big difference in the infrared.
Right. Indeed, so the radial mode, usually they come from radiatively inefficient accretion. So that means their optical or UV luminosities are very dim compared to the quasars. All right, so you might think that, okay.
Quasar mode always isotropic?
Yes. Yes.
So that's not a difference between.
So, kind of. But for the injection of thermal energy, if you use injection of thermal energy for the radial mode, then it's also like pretty isotropic. But the kinetic energy would be bipolar for a single injection. However, the orientation will be randomized.
I prefer using kinetic energy, right?
Yeah, I'll talk more about that in idealized simulations. Yeah. So what I'm talking about here are the implementations of subgrid models used by cosmological simulations.
One last question for this slide. I'm really curious if we apply this threshold. So will we get a consistent population for jetted and unjetted source? For example, 10% of the accreting black hole systems has jets.
Oh, that's a good question. I'm not sure about that fraction seen in cosmological simulations. I think they must have done some comparison, but I don't remember whether they reproduced this result or not. Mm-hmm.
Thank you.
Yeah. All right. So given all these free parameters and free choices of parameterization, actually you can expect that there must be some huge uncertainties involved in these subgrid models. So here I show you one study that I've done several years ago, looking at the uncertainties caused by these different AGN prescriptions on the cluster integrated properties such as X-ray temperature, X-ray luminosity, etc. Those variables often used in cosmological studies using clusters. And what I found is that actually the uncertainty is very big. So even at R500, which is often used in cosmological studies, the uncertainty in these variables range from 15% to 150%. So that means if you want to do precision cosmology down to percent level, then actually the uncertainties caused by these theoretical AGN feedback models is really substantial. And also you can see that the uncertainties are even bigger if you go to cluster centers. So if you want to predict, for example, the star formation rate of the central BCGs and their evolution, then actually you know that your answer would be very, very highly uncertain.
What kind of subgrid models you are comparing?
So like the variation in the accretion models and also the different kind of energy injections. Yeah. So at that time we try to vary all kinds of theoretical models that's used in previous studies. Yeah, and then we found that actually the uncertainties are really large. Alright, so really trying to go beyond the simplistic subgrid model, we must do the following things. So first, understand the subgrid physics better using both high-resolution simulations and observations. And second, to identify a minimal set of essential parameters and build a robust, physically motivated AGN model. So in this talk, I'm going to summarize, focus on the point 1. And for the point 2, of course, it is an ultimate goal that we are trying to reach, and I hope after some of the later discussions in this workshop, we'll have a more clear picture how to proceed. Alright, so this picture nicely summarizes the complex physics that's involved below the scale of around 1 kiloparsec. So ranging from the rightmost side is the scale of the megaparsecs, which corresponds to roughly the size of galaxy clusters. And then kiloparsec scale, which corresponds to the size of the host galaxies. And the parsec scale roughly corresponds to the sphere of influence of the central supermassive black hole, and all the way down to Schwarzschild radius. And as you can see, the whole feedback loop really ranges several order of magnitude and involve the following processes. So first is the supermassive black hole feeding down to the Schwarzschild radius, and also there's what happens around in the vicinity of the black holes and how it converts the accreted resonance energy into winds, jets, or radiation. And then the third process is the generation of winds and how the winds can propagate to kiloparsec scale and affect the star formation rate in the host galaxy. And lastly, how the jets propagate to even larger scales to influence the atmosphere in the galaxy clusters. So in the following part of my talk, I will briefly go over each of these categories and summarize the important findings and open questions. So in terms of supermassive black hole feeding, like I said, previous simulations have used just simple boundary accretion rate with some large boosting factor. And some observational studies have shown that the AGN jet sting in galaxy clusters in some systems is consistent with boundary accretion rate. However, in other observational studies in recent years, some of the observational studies have shown that actually some of the jets are not possible to be fed by the boundary accretion rate. And going back to the theoretical point of view, actually the boundary accretion rate can be rarely met because the derivation of this formula actually assumes spherically symmetric steady-state accretion from fluids with no angular momentum and no magnetic field. So in realistic astrophysical environment, the boundary accretion rates simply do not apply.
But if you have angular momentum and you feel the accretion rate will be lower.
Right, yeah, if you include angular momentum and magnetic field, like what was mentioned, actually, the boundary accretion rate should be even lower. Okay, so indeed, people have been proposing some alternative scenarios. For example, this work, Hopkins and Quasar et al. 2011, they used a set of zoom-in simulations to look at systems with non-zero angular momentum. So they developed a model that applies to gas with some angular momentum, like within these galaxies, mergers, etc. And like any accretion systems, there need to be some mechanism for outward angular momentum transport in order for the gas to accrete and flow into the vicinity of the black hole. And they found that the torque can be provided by non-axisymmetric perturbations to the stellar gravitational potential, such as sparks on the kiloparsec scale, and also lopsided disks on the scales of parsec. And they also derived an analytical prescription that well described the simulated accretion rate. All right, so there at least are some alternative models to model the supermassive black hole accretion with angular momentum. And there's actually another alternative, which is called chaotic cold accretion, or CCA, and it's motivated by the observations of multi-phase cold gas filaments in galaxy clusters. So like what's shown on the upper right here, this is an image of the Perseus cluster. The blue color shows the X-ray images, and the red contains both the radial emission from within the AGN jet inflated bubbles and the H-alpha filaments that's extending to tens of kiloparsecs. So this kind of cold filaments are actually very often seen in observed massive galaxy clusters. So in recent years, there have been a series of works trying to understand what is the criteria for forming these cold gas filaments. And the results looks like something like this. So they found a criteria for condensation or local thermal instability. So basically what they found is that when this condition is met, T-cool over T-free fall or some other dynamical timescale, less than some threshold, then you can see condensation of the coal gas within these clusters.
What's the ionization state of these coal gas? Are they ionized or neutral?
Ionized. So H-alpha, yeah, it traces 10 to the 4 Kelvin gas.
Actually, the SMA observation shows that within the H-alpha, there's also CO molecular gas.
Yeah, that's right. And once these cold filaments formed, actually they can have inelastic collisions, and also tidal forces will cause angular momentum cancellation and trigger and enhance the accretion of the central supermassive black hole. And the simulation by Quasar et al. They showed that actually the accretion rate by CCA can reach approximately 100 times larger than the boundary accretion rate. So this is a pretty promising mechanism for explaining why we need such a large boosting factor in the cosmological simulations. And note that although the CCA was invoked to explain the cold gas filaments in galaxy clusters, but it may be relevant for more violently accreting irregular systems at high ratios too. Alright, so we do have several alternatives to the original simplistic boundary formula But there are still some open questions, including how well does each theory compare with the data? So for the CCA, there seems to be growing evidence observationally where we see that at the center of massive clusters, actually we can see redshifted assorption lines, and indicating that there are some cold clouds that's falling into the supermassive black hole with column densities that's consistent with the CCA theory. However, for the gravitational torque theory, it's not clear whether it has some support from the observations. And ultimately, how the supermassive black holes are accreting is related to this question that observers usually ask. That is, what powers the AGN, right? If you look at certain type of galaxies, do you find higher fractions of AGNs? And the observation seems to be quite controversial. So earlier theoretical studies have proposed that you should see AGNs when there's a merger, but observationally it has been very difficult to establish the link between mergers and the AGN. And therefore, more recently, people have been more and more convinced that maybe the AGNs at lower redshifts are triggered by secular processes within galaxies, and as described by the gravitational torque theory. However, if that's true, then you should expect to see higher fraction of AGNs for example, barred galaxies. However, observational studies have been showing negative results too. Right, so I think it's still unclear whether these theories really is supported by the observational data. And once these theories are tested against the data, then the ultimate goal in this field is trying to determine which black hole accretion mechanism is dominant, depending on the galaxy type and environments. All right, and the second phase in the overall AGN feedback loop is on the scales of the black hole accretion index. And I won't go into details because Hongyi will present a more detailed models on Thursday. So I'll just go over the results very quickly and also highlight some of the relevant findings related to the subgrid models. So on the right-hand side, I'm just showing you the conventional picture of accretion index theories, ranging from low accretion rate to high accretion rate. We have thin disk, or the radiatively inefficient disk. And then we have the standard thin disk for intermediate Eddington ratios. And then for near Eddington or super Eddington disk, is modeled by the slim disk theory. And over time, their theories have been progressed from early analytical results to GR MHD simulations, and then nowadays people can do GRR radiation MHD simulations. So the complexity really grows over time. And there are several successes, including the following. So basically the simulation results have been largely confirmed the thin disk theory in this intermediate range. And for the thin disk, the results are also consistent with the radiative inefficient theory. And also for if the black hole is spinning, then the simulations also found jets are launched as described by the Blanford-Zan mechanism. And for the highly accreting supermassive black holes, they found that the radiation pressure is really intense, and therefore AGN disk wind can be driven due to the large radiation pressure. All right, and in this field, in terms of the AGN feedback model, the goal is to obtain the efficiencies for radiation, winds, and jets as a function of Eddington ratio, black hole spin, magnetic field flux, etc. And note that these GR MHD simulation or GRR MHD simulations are both simple and hard. So it's easy to understand they are hard because they involve really complex physics and they're very, very computationally expensive. But they're at the same time very simple in the sense that they're based on first principles and they're relatively free of free parameters. Unlike larger scale simulations where we have a lot of astrophysical uncertainties. So in principle, we should be able to make progress and get results as long as we have enough resources.
So can this GRHD simulation also explain this the pattern of what for feedback?
They largely are consistent. What?
So can this GRHD explain the previous slide?
Previous slide.
The supernovae feedback? Feedback of the accretion? Or this boundary accretion?
But this is about feedback, right? Or but this is really close to the black hole. Yeah. So how to connect the large-scale accretion to the accretion index theory is also an open question, I think. Yeah.
Because the length scales are
But essentially, we can determine the jet power from the geometry simulation.
Right.
Yeah.
So for these simulations, usually you have to fix some accretion rate and then given an initial magnetic field flux and then black hole spin, and then it will give you an efficiency. But it doesn't tell you how to obtain these initial conditions from the large scale surrounding. So there's still a gap in between. And one thing to note is that these accretion index wind is very consistent with the quasar wind that we've seen in observational data. All right, and the third phase is the quasar wind feedback. And one of the key questions in this field is trying to answer what's driving the kiloparsec scale warm ionized or molecular outflows. And so in order to understand the driving mechanism, people have been trying to answer the question whether this outflow is energy-driven or momentum-driven. And thanks to both simulations and observations, people have found that energy-driven outflows could produce the momentum injection that's seen in observed outflows. And this kind of energy-driven outflow is consistent with the picture that these kiloparsec scale outflows are driven by the accretion index wind, because when the accretion index wind close to the black hole bump into the galactic medium, then the reverse shock will thermalize the gas and create a very hot bubble near the center. And the adiabatic expansion of this hot bubble can then drive the gas outflow at kiloparsec scale. All right, and these works are really helpful in terms of implementing AGN feedback because they justify the use of injection of thermal energy for example feedback.
So this one, can you distinguish with the jet due to the outflow due to the jet?
I think observationally you can only see the momentum boost, right?
Yeah.
And indeed, I think jets, if they thermalized within some small scale, then they could mimic the energy-driven outflows.
Yeah. So.
But jets usually propagate to larger radius, right?
That's true.
Yeah. So this scenario really works if you have thermalization of whatever energy is inputting from the small scales before they reach the kiloparsec scale. And another big question in the field of quasar wind feedback is trying to explain the existence of molecular clouds seen in the observed outflows. For example, early studies have shown that actually the molecular clouds can be easily destroyed within the hot outflows. However, recently, simulations have found that actually by using time-dependent chemistry, they can successfully produce the molecular clouds with velocities that's consistent with the observed outflows. So in terms of quasar mode feedback, we now have some idea of what's driving the kiloparsec outflow. However, there is, of course, some open questions. And one of the key questions is, how exactly does the wind suppress the star formation? So both simulations and observations have been very difficult to find this star formation suppression. And I think TC will mention one case that falls into this category tomorrow. And also another related question is what exactly causes the quenching? So in the conventional paradigm of Quasar wind feedback mode, we think that the gas are ejected away from the host galaxy and then the star formation rate is suppressed. However, simulations have found that it's actually quite difficult to eject the molecular gas away, totally deplete them within the host galaxy. And therefore, some other mechanisms like heating or turbulence have to be invoked. And also, the results might be more complicated because it may depend on AGN luminosity, completeness of the ISM, and geometry. For example, in the recent simulation by Tori et al. 2020, they show that the winds from high luminosity AGNs are able to eject the gas to a significant radius, but lower luminosity AGNs are unable to affect their host galaxies. And they think that the fact that the inefficiency of star formation suppression is due to that their initial condition is looking at a disk galaxy, where the AGN winds can just escape from the path of least resistance and not affecting the galaxy very much. So in other words, their results suggest that if you have some irregular galaxies where it's not lying in a plane, then it's more likely to increase the efficiency of this wind feedback. And another question, so we've been talking about the possible scenario of driving large-scale winds by accretion disk winds, but what is the role of radiative driving on dust on the scale of the dusty torus? So this is an alternative scenario to the accretion disk wind theory. So it's currently still very unclear what is their relative roles in providing feedback. And finally, do jets play a role in quenching galaxies? So some observational studies actually found suppression of star formation, possibly due to the existence of jets. And also the simulations have found that it's plausible to suppress star formation using jets. And therefore, it's important to answer this question, do jets also play a role in addition to the wind feedback? And finally, radial mode feedback. So in the beginning, I mentioned that we can very clearly see interactions between the jets and the ambient intracluster medium, and there's a nice correlation between the heating rate and the cooling rate, suggesting a feedback cycle. So if you put that into idealized cluster simulations, then people indeed find that by including boundary accretion and thermal injections, they can successfully prevent runaway cooling of clusters and reach cell regulation. And later simulations have invoked CCA, the cold gas accretion, and kinetic jets, and they can reproduce the properties of cool core clusters very, very well, like what's shown on the right-hand side. So using this type of purely hydrodynamic simulations, people have been making substantial progress in terms of our understanding of the process of local thermal instabilities, and also about the question of how the kinetic energy of the jets thermalize into heating in the intracluster medium. And this is the work I've done in 2016, which shows that actually the main heating mechanism is the mixing of the hot bubbles with the ambient gas, as well as weak shock heating, whereas other processes are subdominant. All right, and you might think that, okay, the radial mode feedback seems to be more clear, and probably we already solved the cooling flow problem. However, life is not that easy. For example, previous simulations have used kinetic energy dominated jets. However, the composition of AGN jets and bubbles are still highly uncertain, and they can be dominated by cosmic rays. And therefore, it is important to ask, how do they heat the clusters differently from kinetic jets? So previously I've done a series of customary hydrodynamic simulations to try to answer this question, and I indeed find that actually kinetic energy dominated jets and customary energy dominated jets are very different in terms of providing the feeding and the cooling and heating process, and also the dynamical effect and the heating effect will be very, very different. And therefore, it's important to ask the following question: how to distinguish them? How to distinguish kinetic energy dominated jets and customary energy dominated jets? So in my recent work, we suggested a possible observational study that can be used to distinguish these two scenarios by looking at the SE fluxes. So like what's shown here, on the left-hand side is the thermally dominated bubbles, and on the right is the customary bubbles. And as you can see, the SE flux shows depression for the customary energy dominated bubbles. And that's because the SE flux is an integrated thermal energy, thermal pressure along the line of sight. So for bubbles that's dominated by cosmic energy, you should see some suppression of the SE flux similar to the X-ray cavities. So that's one potential way to distinguish the composition of the AGN jets. And currently we're looking at other possibilities to distinguish these two scenarios. For example, you may think that, so because kinetic energy dominated jets should input more momentum to the ambient medium, so they should drive pretty different perturbations in the X-ray surface brightness maps. So that's what a graduate student at NTHU, Lu Chen-Xie, is working on. So he's trying to make mock observational X-ray images and trying to analyze the perturbations similar to the observed Perseus cluster, and to see whether the thermally dominated bubbles or cosmic bubbles are more consistent with the observed perturbations.
Karen, so does neutrino play any role in cosmic ray jet?
I haven't thought about this problem, but neutrinos should be produced if the cosmerays are hadronic, right? And I think it's possible, but I don't know if anybody has looked into the neutrinos generated by the cosmic jet. Yeah, it's an interesting question. And another question is that previous simulations have been using purely hydrodynamic simulation, which assume that the intracluster medium is an ideal fluid. However, the intracluster medium is a magnetized weakly collisional plasma. So how do the plasma particles of ICM affect the feedback processes? In particular, in a magnetized medium, the ionized particles should gyrate around magnetic field lines, and therefore the transport processes should be anisotropic. So I've done the previous simulations including anisotropic thermal conduction, and show that actually convective heating is subdominant compared to other heating sources. So people don't have to worry about thermal convection that much, so that's good news. However, a recent study including anisotropic viscosity shows that actually the plasma effects can be very, very important. So like what's shown on the lower left here. So here I'm showing you the gas density distributions coming from two different simulations. One with traditional Brzezinski viscosity along field lines, and the other is including more realistic plasma instabilities on microscopic scales. And as you can see, the bubble shape are very different, and that can influence the amount of heating that can be provided to the ambient medium, and also the further evolution of the feedback cycle. So this is just to show you that actually the microscopic physics can really influence the macroscopic properties of AGN and galaxy cluster evolution. And another student at NTHU, Hsiang Wang, he's working on quantifying the energy dissipation rate for sound waves by this Brzezinski viscosity and also including the plasma effect. So that will be an important step toward our more complete understanding of thermalization of the AGN jets in a more realistic weakly collisional plasma. Okay, in summary, the state-of-the-art cosmological simulations have had tremendous success in reproducing the properties of galaxies, and AGN feedback is one of the critical ingredients in these simulations. But due to huge separation of scales, subgrid AGN feedback models are necessarily simplistic, and thereby they limit the predictive power of these cosmological simulations. And detailed observations and multiscale simulations have significantly improved our understanding of the supermassive black hole feeding and feedback processes on sub-kiloparsec scales. And here I just put out all the open questions that I mentioned in my talk, and I'll draw your attention to these two questions. So what is the urgent next step to improve the subgrid models? And what additional simulations are needed to answer the open questions or to interpret controversial observational results? I'll stop here. Thank you very much.
Thank you. So, questions?
Thank you for the talk. So you mentioned about feeding to the black hole and feedback from the black hole. So, and cold flow is one of the proposals for feeding a black hole. So if we observationally, if we observe a cold flow, so do we expect that the feedback has not yet taken place, or it can, or not necessary?
Right, it's still unclear how the feedback actually intervene in the feeding process. So from the theoretical point of view, people have been trying to separate these questions because we cannot just put them into one single simulation. So it's hard to tell what really happens in the realistic case where the feedback actually couples to the feeding, right?
And what's a difficult part for related simulation? Is it scale or?
Yeah, scales. Yeah, spatial scales and time scales.
Thank you.
I'm curious about, could you set out the AGN ratio in your simulation, or it depends on the numerical calculation?
I'm actually not sure about what the motivations they have about putting a cap on the black hole accretion rate. I don't know if they don't do it, what will happen?
Maybe otherwise they don't know where to put the energy.
Right. That's right.
And I also have another question. How about the raw dark matter? Can dark matter affect the AGN feedback?
So usually the dark matter only, in this simulation, mainly provides the gravitational potential within these collapse systems. And what's important within and close to the center is the aerodynamic physics that's affecting largely the properties of gas and stars near the center.
Hi. So for the radio feedback, so usually, so we see some cartoons. If we consider galaxy cluster, and usually the radio feedback is contributed from a galaxy located at the center of the cluster. So is there any reason, is it always so, or it could be contributed from other locations as well?
Right. Very good question. So we do see some radio galaxies at the outskirts of clusters, but we do see most powerful jets within near the center of clusters. And that's because they are really required to suppress the cooling. And it implies that there must be some large amount of feeding that's involved near the cluster center. And indeed, from the calculation from the extra cooling rate, we expect that the mass inflow rate should be very, very large for the central BCG.
And usually contributed from a single galaxy, or two?
Usually it's from the central BCG.
Wow. Okay.
Yeah.
Thank you.
So all BCGs powerful radio jets that have sufficient energy or you do analytical cooling?
So I'm aware of observational studies looking at cavities inflated by AGN jet, not necessarily looking at the radio emission, but the bubbles that's seen in the X-ray images. And as long as there's, as long as you're looking at cool core clusters with very short cooling times, there's some bubbles, you know. So it's almost 100%. So whenever it's needed, you find bubbles. Yeah, that's a very strong indication that the radial multi-bag is acting to suppress the cooling.
I'm curious whether these different accretion schemes for the black hole has some direct consequence on the morphology or the properties of the galaxy. I'm asking this because in recent years, people doing protoplanetary disk simulations actually were starting to realize that the inner boundary condition has a strong effect. So we start to realize that all the disks are actually fake. They strongly depend on the inner boundary condition, but I don't know whether this is the same case for galaxies because the accretion velocity should be faster. It is the case in the protoplanetary disk because the accretion is subsonic, but I don't know whether in galaxies there are any difference or similarity.
I think the fundamental question for black hole is that we really don't know what's happening near the black holes. So yeah, the disconnection between what's happening on the galaxy scale down to the vicinity of the black hole. So there's no simulation that can track all the way down to the accretion disk. Yeah. So and normally for like the CCA simulations, they just put an inner boundary where once the materials pass through this boundary, they're accreted. They're assumed to be accreted by the supermassive black hole. So there's no way to understand what's happening below that resolution. Yeah.
So there are some suggestions like considering multi-patch simulation, which you would consider two different length scale in the single simulation, and two simulation paths that are connected by changing the boundaries, connect up to answer this kind of questions.
Yeah, I think that could be doable. But I'm not aware of any studies that have done that. The Hopkins et al. 2011 work is close to what you were suggesting. So they put in zoom-in simulations. So basically they simulate the whole galaxy at first, and then they try to just pick one period of time and re-simulate with much higher resolution down to very small scales. So that's kind of close to in this direction.
But in this multi-patch simulation, the small scale simulation also provides feedback to our small or large scale.
No, they didn't put in any feedback from the small scale back to the large scale.
So actually, regarding Guoquan's comment, actually I saw the European group have done something similarly. Try to using the Galactic and the code chain, like they try to simulate the entire spiral galaxy. But in the inner part, they have a very different setting of the patch. Or actually, maybe a different simulation. And try to do this, and sort of like connecting the two simulations through it's very unique mesh algorithm. And my question is about the cosmic ray. So, in terms of the cosmic ray source, we know like the 10% of supernova explosion might be transferred into cosmic ray. But how about in the AGN case? How much cosmic ray can I get from the AGN jet, and what kind of spectrum may it be like?
Like I said, the composition of AGN jets is highly uncertain. So basically, there's no first principle theory that can tell you what the composition of the AGN jets should be. So we can only infer them from observational studies. And people have been looking at the composition of these bubbles inflated by jets. and the composition that inferred is such that it can be either dominated by very, very hot thermal gas or customary proton. Yeah, so the jet likely has to be hydraulic.
So that would mean that there should be, if it's cosmically dominated, then there should be a corresponding neutrino emission.
Yeah, maybe. I guess it depends on the energy of the cosmerays.
Right.
Yeah.
So in principle, one can do a calculation and try to estimate what would be the estimated flux on ice cube.
Yeah. I think Ke has done some calculations related to that, but I forgot the results.
And do we need to parameterize the location of shock? Is it necessary to have a shock in a jet?
Which case?
A cosmic ray jet.
Oh, shock.
Acceleration side, you mean?
Yeah, acceleration side.
Oh. So I guess the question is where the cosmerays are accelerated, and that's very, very unknown. Yeah, it could be very close to the accretion index and then propagate all the way to large scales, or it could be that initially it's leptonic dominated, and during the entrainment process, by propagating to the large scales, they become more and more heavy. So either possibilities could be true.
So you mentioned about you're working on some cosmic, you're a student working on some cosmic ray jet. So what's the setup for modeling cosmic?
So we're currently only modeling the dynamics of the cosmic rays. So we're only considering the pressure effect that it can give. And basically by injecting energy into kinetic mode or cosmic mode, for different adiabatic indices and also the momentum, it can cause very different results. So that's what I meant by doing simulations, trying to distinguish these two scenarios. So we're looking at the dynamical effect of cosmic rays, but not distinguish their composition or energy spectra, things like that. So we're treating cosmic rays all together, assuming that the jet energy is dominated by cosmic rays instead of kinetic energy. Yeah.
What kind of cosmic ray energy density do you need for cosmic rays to dominate the if the cosmic rays are dominating the dynamics of the jet, what kind of energy density?
I don't have but the feedback energy is basically determined by the accretion, right, in these simulations. So the typical jet power is 10 to the 45 ergs per second, and then depending on the duration of each injection, you will inject different amount of cosmic rays.
I guess my question is like, how far does it have to dominate? How much does the cosmic energy density have to exceed other energy densities, or does it dominate?
You mentioned circular evolution in galaxies, and as far as I know, people usually also discuss galaxy merger as a possible scenario. So what's your opinion, or have you considered it in your simulation to treat AGN or vice versa?
I have no preference from the theoretical point of view. As long as observers can tell me which model to use, I would be very, very happy. So yeah, like I said, earlier studies have suggested mergers as the dominant power and mechanism for AGNs, but there seems to be very difficult to establish this link, and therefore people have been suggesting secondary evolution.
This is a point I understand. I thought for example, Mueller, in the late merger state, when the AGN fraction is higher and higher.
So people say that for really high luminosity AGNs, there might be a difference. So there seems to be some association studies suggesting, indeed, for high luminosity quasars, it's true that there are more AGNs in mergers systems. Yeah, but for lower luminosity AGNs, it's not obvious. There's no obvious distinction between merging galaxies and normal galaxies. Right.
So is static swapping without playing a role in AGN feedback?
The amount of energy is quite small. So it's probably not enough to influence the whole galaxy on the galaxy scale.
Right. Can trigger the AGN activities somehow?
I think yeah. But there are like more smaller injections of energy. But I don't know if people have considered the cumulative effect of TDEs in terms of galaxy evolution. Right, I don't think people have considered that.
So, Albert, I have a undergraduate student actually try to do is consider TD feedback in the galaxy evolution. And the way he try to dumping the energy every 100,000 years, that's when TD occurs, and about 10 to 52 Earths, 53 Earths, and then also consider with or without AGN at the center. And actually, then we evolved several billion years, and then eventually we got all the physical quantities, star formation history. Actually, doesn't change much. So the feedback is actually sort of even weak up. Yeah. So that's a student's mind. Another question is, if the two galaxies are mergers, and each of them has a supermassive black hole at the center, and this goes to the final state of the merger of the two supermassive black holes, what kind of feedback or what kind of AGN might occur in that kind of situation? So you two black holes are mergers, and there's a lot of mass surrounding. Where probably accretion will occur along the way when they merge.
That's the earlier proposal that mergers are triggering the quasar, the Tsing. However, at lower redshift, it's not obvious whether mergers have any connection with the onset of AGNs.
There are two kinds of mergers. You have wet merger and dry merger. I think only wet mergers trigger the quasar. Dry mergers probably you can only have radial or AGN. Yeah, then these are little gaps.
Would that be possible to have for example, two jets coming from center of one galaxy? Due to you get the two of the black hole, they merge into the new center of the two galaxies. And each of them are accreting mass. Okay. Yeah, that's my guess. Is that a possibility? Does anyone observe there's two jets on one of the?
There are very few exist actually. Yes. And I think if EHT can observe for a long time, I think maybe track the rotation of the two AGNs related to each other.
You see many cases that you have double jets, right?
Yeah. But the really resolved one, as far as I know, only one or two. Really core. There's two core with both jet showing up.
Okay, so any more questions? Comment?
So what's the budget next step?
That's the questions for you guys. What do you think is the most urgent next step for improving these theoretical models?
So from data you also explain some better microphysics simulations. Do they agree with subgrid model or
understand the microphysics better and trying to come up with a prescription that can be used in these large-scale hydrodynamic models.
So can this small-scale simulation maybe constrain some of the lower limits of the subgrid parameters?
Yeah, that's what we're trying to do. So trying to parameterize the effects from radio feedback, for example. Yeah. But even on the smaller scale, there are a lot of uncertainties, like the composition of the jets, yeah, things like that.
Yeah. So there's no any initial simulation.
Right. Because the large scale, there's really no first principle simulations that can really connect all the physics together. That's the difficult part of understanding AGN feedback and feeding.
In your jet simulation, when you put in a cosmic ray, do you have to assume any kind of accretion mood or feedback, or do you just simulate the jet?
Right, so we work in the hypothesis that the black hole jets are triggered by black hole accretion by the cold gas, according to the CCA scenario. Right, so in our calculation, we can resolve the cold gas, and then we can calculate how much cold gas is available to feed the black hole, and then we can then convert the created energy into feedback into the jets.
So in your simulation, is the jet power mainly come from accretion?
Yes.
But how about black hole spin?
Right. Oh, okay. Yeah, I haven't listed black hole spin on this slide, but black hole spin is kind of omitted in all these kind of studies. So yeah, that's a huge uncertain parameter in all these cosmological larger scale simulations.
So in terms of acceleration of the particles, right? So I wonder, CCA as opposed to another mechanism that is different. So I forgot the name.
Gravitational force.
Yeah, gravitational force. Yeah. So I wonder, in these two scenarios, what kind of environment do they give to so that it favors the acceleration side? Like, in these two different scenarios, CCA and the gravitational torque scenario, will they give a different initial condition to such that it favors particle acceleration, be it shock or anything?
So those two mechanisms are explaining the feeding of black holes, right? And usually the velocities of these accreting clouds are not very large, so they don't necessarily drive shocks, right? So shocks are usually driven by the feedback, wind or jets.
At a larger scale.
Yeah.
I guess on the issue of impact of AGN on host galaxies, from an observer point of view, we're facing difficulty of converting, for example, the observed outflowing gas to the mass loading factor, for example. And
because
that's
of the
depending on
different phases.
Yeah, it's also multi-phase as well as the geometry, because people always assume spherical symmetry, right? Which, I mean, for your simulation, must be not true.
Right.
So I guess on the first question, what's the next step? I guess perhaps the simulation could do the observer a favor to kind of sort of explore what kind of morphology of the outflowing gas could be. So once we observe an outflow gas, we have a geometry example that we can assume.
Yeah.
So we can calculate the mass loading factor more precisely or more accurately.
That's a good point. Yeah.
The other one is the energy, the coupling efficiency is the energy feedback from AGN to the atmosphere of ICM as well as ICM. As you said, there's radio jets punching the hole to the ICM, but how much of that energy actually propagates to the medium, and what's the time scale of that? I guess simulation could probably tell us more about this.
In that sense, that I'll give a talk about the spatial resolved molecular gas AGN jet interaction results.
From an observational point of view.
Yeah, with my talk will be the radio mode feedback within the kiloparsec scale.
Right.
Yeah.
But yeah, once you observe that, but how do you know how much energy actually got dumped into the galaxy? Because that would be related to the suppression of starting, for example, or the post-galaxy
one case I will show. Yeah.
Oh, you got a handle on that. That's nice.
How much jet feed the energy into molecular gas.
Oh, nice. Okay.
I actually have a question about the morphology you mentioned. I wonder, because the molecular outflow is in kiloparsec scale. So I wonder whether a high reaction ALMA will provide you the resolution to resolve the molecular outflow, and I will give you information.
I will show in my talk.
That's great.
But I will not be able to attend your
Yeah,
talk.
sorry about that. You invite me to the Kaohsiung.
Any more comments? Suggestion from observers? No? Okay, if no more questions, then thanks Karen again. So I believe this is the end of today. So is there any announcement from LC?
So
There's no workshop dinner.
no, unfortunately, because of this COVID-19, since we cannot invite international speakers, so this workshop therefore is considered as a domestic workshop. So the budget scale. So that's why we not budget.
Bento box.
So yeah, just tomorrow again 10 o'clock.
So tomorrow we will start at 10.
Yes.
很多问题要解决。
没有啊，去找我小孩。跟他们去回家玩一下，对。这游戏干嘛？
充满未知数。可以，对啊。下次联络。你可能跟那个 SMBH 说 Galaxy 把它结合起来，然后里面的一个最新。对，可能最里面那个 subgrid 要等看。